Hi class, here's another example problem. Vitamins are often categorized by either water soluble or fat soluble. And we've got some images of fat down below. We want to explain why vitamins A and K are fat soluble. So A and K are fat soluble, and vitamins B and C are water soluble. We've got our Lewis-Dot structures of a fat molecule shown down below. So the fat-soluble one, fat-soluble vitamins should be soluble in something like this. You can see that this is mostly nonpolar. There's a lot of hydrocarbons in there, and the only dipoles that are in this actually cancel each other out. So this is definitely a nonpolar molecule. And we know that water is polar. Okay, so that is nonpolar, and we know that water is polar. So taking a look at our diagrams up here, the ones that are fat soluble are vitamin A and vitamin K. Then we have vitamin C and vitamin B that are water soluble. Let's pay attention to some important parts of these molecules. On vitamin C, I can notice an OH bond here, 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 and here. We've got some other dipoles, but those are very, very strong dipoles. Okay, when I look at the vitamin B, I've got an OH bond here, an OH bond here, an OH bond here, several OH bonds, and there's also some oxygens that form dipoles. Okay, there's an oxygen here that forms a dipole. Not as strong of a dipole as an OH bond, but it's there. Now look at vitamin A. There's one OH. Look at vitamin K. Well, we've got two of those somewhat weaker oxygen bonds, carbon to oxygen bonds, not particularly polar. Okay, so this is more nonpolar. This one's also more nonpolar. And vitamins C and B are more polar. So if we wanted to give an explanation for this, really, it's just that a more polar molecule, like vitamin C and vitamin B, are going to have a stronger interaction with a water molecule because of the dipole-dipole forces, and also because these are OH bonds, we've also got some hydrogen bonding taking place. Where in the vitamin A and vitamin K, it's mostly nonpolar. There's a small polar section on vitamin A, but the biggest part of vitamin A is actually nonpolar, which causes a lot of LDF, a really strong LDF interaction between it and a large nonpolar molecule like a fat. So, vitamins C and B can form hydrogen bonds with water molecules. And vitamins A and K can just form LDF with fat molecules. These large fat molecules. Now the other thing that could happen is it could form dipole-induced dipole forces with water, but dipole-induced dipole is a very, very weak interaction, so it wouldn't actually be enough to separate water molecules or to separate vitamin A or vitamin K molecules from one another. So let's look down here. Methanol is much more miscible in water, while N-butanol is much more miscible in hexane. We want to explain why, comparing the interparticle interactions and strength. Well, methanol is a fairly small molecule that's polar, and it's got an OH bond in it. In butanol, it's still got that OH bond, but you see this long non-polar chain? Okay. So what we would say is methanol is a small molecule. It's a small molecule with a strong dipole. And it forms, as a result, it forms stronger IMF with water, specifically hydrogen bonding. But if we look at N-butanol, it has a much larger nonpolar section, which allows it to form strong LDF, London dispersion forces, with hexane. It has similar intermolecular forces to hexane, more so than to water, and that allows them to dissolve one in another.